Now we want to move on to acid-base reactions. So precipitation reactions we already covered. We're exchanging ions between compounds. That's always going to be our pattern. We just say, what are the cations, what are the anions, swap them. We can recognize that this happens when we react two ionic solutions as our reactants. We have that double displacement pattern, which allows us to predict products. That's what we want to be able to do with reactions. Acid-base reactions offer a similar reaction idea. In this time, instead of exchanging any sort of ions between compounds, we're going to be exchanging H+ ions between what we call an acid and a base. So we want to talk a little bit about what acids and bases are. This is a dominant classification of molecules and compounds. Acid and base properties are really common. There's a whole chapter in the book, chapter 14. If you come back for Gen Chem 2, we'll spend weeks talking about acids. And acids and bases react via what's called a neutralization. So acids are kind of defined as the things that react with bases. Bases are the things that react with acids. So these are paired. Their definitions are always going to be linked together, and they're defined by reacting with each other in what is called neutralization. Things that are acids and things that are bases also interact commonly with everyday life. A lot of the food you eat is acidic because acids tend to have a sour taste. We don't eat a lot of bases because they are bitter. But they also are really good at cleaning. So soap, baking soda, which we use for cleaning, bleach, ammonia, these things are all, oven cleaner is a very, very good base. So generally bases are a little more aggressive as far as humans go. The acidic things that we deal with, like lemons, are really, really good acids there. They just have a better taste as far as humans have evolved. Bases are pretty gross. They also do feel slippery. That has to do with them actually reacting with your skin and creating a slipperiness. Soap is slippery, but if you touch, say, like bleach, it makes your skin slippery because it's turning your hands into soap. The oil on your hands into soap. I should note that these sort of descriptions and properties of acids and bases we do not rely on in the chemistry lab. That is sort of a, in your life, we're not tasting things, we're not touching chemicals to see what they are. So a little bit of terminology that can get a little tricky. When we talk about acids and bases, that is a property of a chemical. So nitric acid has the formula HNO3. That is an acid. It reacts as an acid. Sodium hydroxide, NaOH, is a base. That's a property of a chemical. When we start talking about the adjectives acidic and basic, that refers to the property of a mixture. So if you have a solution of nitric acid in water, that would be an acidic solution. If you dissolve sodium hydroxide in water, you create a basic solution. So those sorts of descriptions. Nitric acid is not acidic, it is an acid. Acidity and basicity are the names of the property. So again, nitric acid doesn't have acidity, it just is an acid. A nitric acid solution has acidity. Lemons have a higher acidity than grapes. Alkaline is another word for basic you may have seen. So for example, alkaline batteries are full of base. They are pretty gnarly on the inside. Alkaline lakes are also a thing. If you've ever been done any traveling, alkaline lakes, the water is very basic in an alkaline lake. So acids, for our definition, are going to be molecules that when they dissolve in water, they produce H+ that is dissolved in that water. So we know hydrogen is atomic number 1, so that's 1 proton. So in a neutral hydrogen atom, you'd have 1 proton and 1 electron. H+ means you take away that electron, so you just make a proton. That's all you get. So when this falls apart, we create H+. So that's why this is a unique kind of ion. It's also just like a subatomic, or a very fundamental subatomic particle. And so that's what we have for acids. One of the aspects of that is that all acids have hydrogen in them. If you're going to produce H+ when you dissolve in water, there has to be hydrogen in the molecule. So the generic formula for an acid is just going to be then HA. So we have this HA where the A, there's no element that has A as a symbol. In this case, the A just means the rest of the molecule. So it could be 1 atom, 3 atoms, 10 atoms, whatever. But whenever we're writing the formulas for acids, we always put the H first. Almost always. I should correct myself. We almost always put the H first. Whenever we see an H in the front of a molecule, that certainly means it's probably going to be reacting as an acid. And what ends up happening is, say the molecule, if you have your HA, it dissolves in water right up on the line, and then you get the H plus, and then everything else, the A, becomes A minus. So it's like you're creating ions. This is still a covalent compound. So for example, if you look at these examples like HCl, that's definitely a covalent compound. Those are two nonmetals. This is a unique property of what happens when they dissolve in water, that they fall apart and create ions. But this only happens in water. Similarly, HNO3, you get H plus and nitrate coming out the back end. The book, I should note, talks about H3O plus, which is called hydronium. We're not going to worry about that. We are just going to deal with H plus for our world of acids. If you come back for Gen Chem 2, don't worry, hydronium makes a very large appearance, but we're going to stick with H plus. Also important to note that all acids are soluble in water. So when they go into water, you would always get AQ. This idea of falling apart, we'll see, isn't always true, but they're always going to be aqueous. So you could easily see HCl AQ, that they're always going to be that present there. And I guess I should also note this H plus, as noted, it is a proton. So they are extremely reactive. So if you dissolve, the reason why acids do chemistry is that if you have that H plus dissolved in water, that is extremely reactive. And so anything you put into that solution that it can attach onto, it's going to. It's going to react really quickly, really readily with just about anything you can find. So I want to talk a little bit about naming acids. And acid naming is going to be based entirely off that resulting A minus anion, right? Once the hydrogen left, you had an anion left over, and that anion name is going to derive what the name of the acid is. And it's actually all based around the suffix on that anion. If you remember, we said that ions that are monatomic usually end in IDE, ATE, and ITE then affect or indicate polyatomics. So based on that, if we have IDE, we use hydro in front of the name of the polyatomic, and we replace that IDE suffix with ic. If we have ATE as the suffix on the polyatomic ion, we take that off and we just add in ic. If we have ITE, we replace the suffix and add us. And then we add acid at the end. So let's look at some examples, because that's a little, these are the rules you can always use, though, but let's look at some examples. So if we had, for example, HBr, if we took out H plus, we'd be left with Br minus, which we'd call bromide. Okay, we'd call that bromide. So the IDE leads to, we turn this into IC. We take off the ide and turn it into IC, and then we add hydro out front. So hydrobromic acid. Whenever we have IDE, we change the ending to ic, and we put something on the front. If we end with just ATE, so for example, if we had perchlorate, we take the ATE and turn it into ic. Okay, so ATE, we have that same ic ending, so we'll note there are two of them. The difference is whether or not you put the hydro in the front. That corresponds to ide, so bromide becomes hydrobromide. Perchlorate just becomes perchloric, not hydroperchloric. We can see similarly, chlorate becomes chloric acid. And we can see that's one of the differences, perchloric and chlorate, and chloric, so that's why the per is used. Chlorite becomes chlorous acid, and hypochlorite becomes hypochlorous acid. Okay, so we got some rules we can follow for whenever we want to name acids. So bases are the counterpart, and bases produce OH minus when dissolved in water. So if we had acids made the H plus, bases make OH minus. And generally there are a couple of other varieties beyond this that, again, there's a lot of acid bases. Gen Chem 2 has a ton of acid base if you want to learn more. But for now, we're going to say soluble hydroxide compounds, because the best way to produce hydroxide in solution is to take an ionic compound containing hydroxide, dissolve it in water, and then boom, you've got hydroxide in solution. So all of your alkali metals, lithium, all the way down to rubidium, any cesium, those can dissolve. Those hydroxides can dissolve, make hydroxide in solution. Hydroxides are otherwise a little difficult to get into solution, but calcium and barium hydroxide are also soluble. So you're just looking for, you use the solubility rules to determine if a compound containing hydroxide is a base. And again, just like the H+ was really reactive, hydroxide is also very reactive. So any solution that's basic, as in you've had base has been added to it, has a bunch of hydroxides, it's going to be very reactive, like say the drain cleaner you use or oven cleaner, anything like that. So when acids and bases react, that's called neutralization. And the process for neutralization is always going to be, we have our acid, H with the A, our base, which is B with the OH. And what ends up happening is the H and the OH combine to give you water, H2O. The A was an anion, goes right there, and the B on the base goes right there. So we can see that we get this interaction where we get this swapping. We're always going to make a salt and water. That is always our pattern for neutralization reactions. If we rewrite H2O as, say, HOH, which is not correct, but if we rewrite it in this way, we can see this is following a double displacement pattern. Acid-base neutralization reactions follow that exact same pattern that we already saw for precipitation. This is still going to be double displacement, and the only thing is that the H+ and the OH- swap. They still do that same swap. We just don't call it HOH because it's become a covalent compound. We call it water. And the thing that's unique about acid-base chemistry is that those two ions are always involved in the swap, H+ and OH-. And it happens so much that it gets its own name. But it's not a precipitation because you're not making a solid, you're making liquid water. Let's take a look at an example. Write an equation for the aqueous reaction between HNO3 and calcium hydroxide. We want a chemical equation. So what are the reactants? It's going to be HNO3 and calcium hydroxide. What are the products? Well, I want to think about what kind of reaction it is. When we identified precipitation, that was because we had two ionic compounds we were reacting. At this point in time, when we see an H in one of our reactants and we see OH in the other reactant, we should immediately be jumping to neutralization as the process. This is the most likely thing that will be happening. This is likely a neutralization process. Then we just need to balance it and add phases. So let's see what that actually looks like. Let's work it out. We want an equation for the reaction between HNO3 and CaOH. So again, write an equation. We're dealing with chemical equations. We're going to need reactants and products. We are given our reactants. I think I dropped it here, but aqueous reaction. So these things are dissolved. You can also look up that that's aqueous or soluble. Calcium hydroxide is soluble. So my question is, what are the products? When we're looking at this reaction, we're looking at these reactants, the things we want to key in on are the H and the OH. When we lead with an H, that means acid. When we see OH, that's OH-, that's going to mean this thing is a base. This reaction is going to be a base, or an acid-base reaction, called that neutralization. What that means is we're going to do a double displacement type idea. H is going to go with OH, and the NO3 is going to go with the Ca. So we're going to write that stuff out. We'd say we get H, which if we think about this, that's like the NO3 becomes NO3-, and the H becomes H+ because it's an acid. And over here we have OH-, and here we have the Ca2+. And so what we need to do, these are ionic, we could think about swap them, but the one thing we want to key in on is right there, I got H plus and OH minus. That makes, if those combine, that gives me H2O. Ca2 plus and the NO3 minus. Get that in there, sorry. Those are ions, they can swap. We do want to be careful, I've written them backwards, but the cation still needs to go first in the actual formula. So that's a 1 comes on the calcium, a 2 goes onto the nitrate. 2. And so again, we just get our formulas, which is the starting point for moving forward, determining what exactly this reaction is finishing up. So we're going to we start with nitric acid and calcium hydroxide, make them nitrate and water. One quick note, whenever you identify an acid reacting with a base, you should expect to make water, check, and a salt or ionic compound, double check. So whenever you think you're dealing with an acid-base reaction, if you see OH, if you see H in the front, one of the products better be water, and the other product better be an ionic compound. So looks like we did a good job here. We got it nice set up. That looks like we're following the right idea. So far, so good. So the next things we want to deal with are phases. And so calcium nitrate is an ionic compound. And so again, we're going to come in, use our solubility rules. Calcium doesn't have a rule, but nitrates are salt, meaning that gets an AQ squeezed in there. Didn't really leave myself quite enough room, but there's an AQ in there. Water, this is the most common phase mistake. You AQ, 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 AQ. Water does not dissolve in water to make an aqueous substance. It instead is a liquid. So you may seem kind of silly. Of course, water is a liquid. When you're in there working problems, coming up, that is the most common mistake. I guarantee it. It's a mistake I made. It's a mistake many people make. Let's just try to make that mistake now, maybe in participation or in some of the homeworks and not in the test. But yes, water is a liquid. We want to be sure we pick that up. So we got our compounds, check 1. Got our phases, check 2. Now we got to balance it. This is not a balanced equation. If we look through it, the H's are going to be a pain to balance, but we can deal with, say, the nitrogens. So I got 1 nitrogen in this molecule. That's the only thing on the reactant side. I got 2 nitrogens over in this compound. So I need, we'll go ahead and use a different color to balance. We'll write it all. But you can see I got the 1 right here. So I need 2 HNO3s. If I look at my calciums, they're balanced. The H and the O, I do want to save for the end, just because how complicated it is. So I balanced the nitrogen first, that helps me. The calciums are already good. So now I will turn to the hydrogens. So I got 2 hydrogens right here. And the reason why I choose hydrogen over oxygen is because hydrogen at least only shows up in one product. Oxygen is in everything, whereas hydrogen's only product. So hopefully I need to put a coefficient in front of this one and we'll be able to move forward. So I got 2 hydrogens right here. I got 2 hydrogens right here. So 2 plus 2 is 4. I got 2 over here. So that works out for what we're looking for. I need an extra. So I have 4 and 2. So this needs to be multiplied by 2 to get me 4 total. So that's messy. Let's rewrite this. Get a cleaner format. It's going to be 2 HNO3 aqueous plus 1 CaOH2, also aqueous, becomes CaNO3 2 aqueous plus 2 H2O liquid. So we make liquid water. So when we're looking at this, we want to recognize acid-base reaction. Acids have the hydrogen up front, bases contain that OH. They follow this double displacement pattern. In this particular case, it's called a neutralization reaction. It's the same idea as precipitations we saw. You just swap partners. You always expect to make water, and then basically the other ions there that aren't the hydrogen and aren't the OH,
form a salt.
Participation 612, question 3. Write the chemical equation for the aqueous reaction between HClO3 and KOH. This is the third question on participation 612, due Friday, June 12th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, write the chemical equation for the aqueous reaction between HClO3 and KOH. Yeah, there's a participation question in this video. Got a couple more videos. This is more net ionics in the next one. See you there.